Okay, so as Janice mentioned, my name is Scott Harmeier, and I'm the Process Optimization Manager for Archer Daniels Midland, or ADM for short. A little bit about what my group does. We are responsible for managing various optimization-related technologies that get applied to our process operations throughout the company. So traditionally, these have been things like instrumentation, process information systems, and basic and advanced process control. You know, those technologies have been available for quite some time, and we've used them quite a bit to try and optimize our operations. But moving forward, we're also moving into areas such as operational intelligence, operational analytics, operations management. So my group is trying to take a more proactive role so that we are really at the leading edge of rolling out those technologies. For those of you that don't know what ADM does, we are a large agricultural processing company with a pretty significant global footprint. We have over 700 grain procurement facilities and/or processing facilities throughout the world. And many of those are connected by a pretty extensive global transportation network. So as you can probably imagine, there are a number of possibilities to use analytics to improve our operations. The question is, what analytics should be applied, and where should they be applied? So, you know, today the term analytics is used so frequently, right? It's probably one of the most common buzzwords you hear today. So, and I think for a lot of people that can be confusing. They don't really know what the term means. So this morning I decided to take a look and see what Wikipedia had to say about analytics. It says, analytics is the discovery, interpretation, and communication of meaningful patterns in data. That makes sense. Pretty simple, right? But again, there are so many different types of analytics that can be applied, and which is why I really like, as we become more descriptive with these different types of analytics, such as operational analytics. So to me, the term operational analytics means analytics applied in real time to manufacturing or processing operations. So I'm going to zoom in now on one of our particular plants. It's a bioprocessing plant that makes a number of different amino acids and other products mainly from fermentation. So one of these products is lysine. It's a bacterial fermentation that we use as an ingredient in many different types of animal feeds. This is a very, very high volume, low margin product for us. And the problem with products like this is that when the margin is low, our asset utilization doesn't look very good because it takes a large number of assets to produce a very high volume product. And as of late, the margins have been very, very poor, and this has not been a very profitable area for us. The positive side of that is it really takes only small incremental improvements in margin to make a big difference. So the purpose of this case study was to try and optimize lysine production using automated analytics with machine learning. Our goal was to, I would say, really optimize the production time. So a lysine batch generally takes between 60 to 80 hours to complete. And what happens is, at some point in that 60 to 80 hour window, the operator decides it's time to stop inoculating the fermenter with feed, and then he waits for some sign that is probably different from operator to operator to decide, okay, this batch is over, I can harvest. So our goal here was to be able to model the progress of the fermentation and to be able to predict when the fermentation was reaching its end. So the operator could see that and not run the batch longer than it needed to be run. Now, I mentioned creating models, and using those models to predict the behavior of a process. And I think it's important to point out that we have been using that philosophy for a really long time in the form of model predictive control, right? And I'm sure many of your companies have been doing this same thing. So I think it's worth a look at seeing some of the differences in features behind what we call model predictive control and what we're considering automated analytics. Generally, model predictive control is based on a fixed set of variables that have linear models between them, and we're making predictions over some fixed time horizon. Model building is generally a manual process. It takes people with strong process knowledge, process engineers, process control engineers, to develop the model and make sure that it makes sense. Finally, once the models are built, they're pretty much fixed, and if anything changes or new constraints are added, we have to do a reevaluation of that model. And that's okay, because the technology is well established. The people that are managing this technology are process experts. They understand all the variables that are involved and the interaction between them. Now, when we move to automated analytics, it's really based on, the predictions are based on anything, any relevant input that happens to be measured in the process. Nonlinearities are generally not a problem. And so the model, because it's looking at all these different factors, is able to achieve a higher level of accuracy. Now, one of the things that I think differentiates the solution we're looking at is this concept of automated analytics, which means that the models are continually updated and are being improved all the time automatically. So Janice mentioned that the data scientist role is growing at an 11% growth rate, right? What growth rate do you think the application of predictive analytics is growing? Much, much higher, right? So if we think of, as a company, if we think of going from basically no operational analytics to potentially thousands or tens of thousands of models, it's very hard for me to imagine having a team of data scientists, an army of data scientists really, on hand to maintain all those models. So I think some level of automation when it comes to these analytics is a very, very important feature. Okay, so now I'm going to go over a little bit about the architecture of the solution. It starts with the OSI Soft Pi system. That is pretty much the foundation of everything we do with process data. All of our process data is collected via Pi, aggregated via Pi. We build basic process analytics using it. So it's really the collection, organization, and contextualization layer of our process data. Once we have the data properly aggregated and organized, we need to publish it. And there we're using the OSI Soft Pi integrator for business analytics. I really view that tool as a context converter, right? We're taking time series data, we're taking asset data, and we're transforming it into a relational format that is consumable by all these various analytics packages. For the actual automated data modeling and prediction, we're using the data platform for validation, prediction, modeling, selecting the right variables. We're generating predictions of how much lysine we're producing over 1 hour, 2 hour, 3 hour, and 4 hour future increments. The output from those predictions is then written back into the Pi system as future data, which means values that contain timestamps into the future. So if you look at this architecture, obviously there are some complexities that go along with it, especially in the modeling area. And as you would expect, I mean, that's expected, right? Because fermentation, any biological process, is extremely complex and extremely variable. And being able to model that accurately can be very difficult. But one thing we got to keep in mind is that we cannot take that complexity and move it to what the operator sees. What the operator sees has to be very, very basic and very simple. It has to be able to be something that he can see, understand what's going on, and take action. In my mind, this is really driving a change in behavior, behavioral-based process control, if you will. So next I'm going to show what this dashboard looks like. Again, we have the results presented here in PyCoreSite. We're using that for the visualization. You see two trends. The blue trend is the actual lysine production as it's occurring over time up till what we consider current time. The orange line is the prediction of that lysine production. So what would normally happen here is the blue line goes up and reaches some level, and then it might level off for some time. And eventually the operator sees that, okay, nothing's happening. I can look at stopping this fermentation. Our goal is for them to see a display like this. And even though if you ignore the orange line, it would appear that the blue line might be continuing at an upward trajectory, right? But based on the prediction, we can see, okay, this is now, but right now I'm predicting I'm done. My fermentation is over, right? It's flatlined into the future. So what this allows us to do is end this fermentation right now, even though it appears that it might still be increasing. We can stop it right now instead of waiting 4 or 5 or more hours for completion. Another interesting benefit, I think, this is another batch of, and again, the blue line is still lysine production. So somehow, in the middle of the batch, we managed to deproduce some lysine. How's that happen, right? Well, our calculation to determine lysine production is based on the concentration that's currently in the fermenter, which is a lab analysis. And I'm sure everybody knows that lab analyses are always 100% perfect, right? Always. The problem is when you get an anomaly, what we've seen is a lot of times operators will react to that anomaly. And that overreaction will actually cause increased process variability. It would have been better if they would have just done nothing. So given this trend, if we had a prediction that was overlaid on top of it, prediction might look something like this, and that gives the operator really something, it serves more as a reality check to the operator. He sees something, not sure if it's right or not. If the prediction is not telling him the same thing, it allows him to question whether action is needed or not. So the next question becomes, how much value can we get through the application of this technology? And here's what I'm trying to do. So the red dots indicate, from a statistical perspective, how much lysine I've produced in each batch divided by the amount of time the batch took to complete. You can see we have a fair amount of variability in that value. So what we hope to achieve is through the application of the predictive models and getting better information to the operator in real time is to replicate our good behavior more of the time, reduce the process variability, and shift our average toward the more profitable direction. Which in this case equates to about a 5% increase in productivity. So what does that mean? Really, that's a 5% increase in asset utilization. And it gives us a number of options now on how we can increase profit. Potentially, we can make more lysine, right? provided there's a market for it and provided our downstream operations can handle it. If that's not available, if I have to maintain the same production I do today, perhaps I can do it with less batches and save money that way. Regardless, either way, with this high volume product, we're looking at potentially hundreds of thousands of dollars a year in savings on this one application. So now if you go back and remember that first slide I showed you of all of our assets across the world and extrapolate that kind of savings across the entire enterprise, it's staggering the amount of opportunity that's out there. So similar to what Janice was talking about, there are a number of different areas to where we could apply this technology, each with a slightly different application, each with a slightly different goal. But the reality is this has so many different applications across an enterprise and tremendous potential to save a lot of money. That's it. Thanks.